Welcome to the fascinating world of remote sensing. Remote sensing is both a science and an art, focused on gathering information about the Earth's surface without direct contact. Instead of being on the ground, we use sensors to detect and record energy that is either reflected or emitted from objects. This process allows us to analyze, process, and apply the information for a variety of purposes, from environmental monitoring to urban planning. Throughout this video, we'll explore the key elements that make remote sensing possible, how it works, and why it's so important in our modern world. Let's begin our journey by understanding the basics of remote sensing and the role it plays in observing our planet from afar. Remote sensing involves a sequence of 7 essential elements. First, there's the energy source or illumination, which provides the electromagnetic energy needed to observe a target. Next, radiation travels through the atmosphere, interacting with particles and gases along the way. Once it reaches the target, the energy interacts with it, depending on the properties of both the target and the radiation. After this, a sensor records the energy, which is then transmitted to a processing station. The processed data is interpreted and analyzed, and finally, the information is applied to solve real-world problems or reveal new insights. Each of these steps is crucial for transforming raw energy into meaningful knowledge about our planet. Every remote sensing process starts with an energy source. Most often, this is the sun, which emits electromagnetic radiation that illuminates the Earth's surface. Sometimes the energy comes directly from the target itself, especially in the case of thermal or infrared sensing. The energy source is fundamental because without it, there would be nothing for sensors to detect. Whether it's sunlight or another form of electromagnetic energy, this initial step sets the stage for all subsequent interactions and measurements. Understanding the nature and behavior of the energy source helps us interpret the data collected by remote sensing systems more accurately. As electromagnetic energy travels from its source to the Earth's surface, it must pass through the atmosphere. This journey is not straightforward. Particles and gases in the atmosphere interact with the energy, causing it to scatter or be absorbed. These interactions can happen twice, once as the energy travels to the target and again as it returns to the sensor. The atmosphere acts as both a filter and a modifier, influencing which wavelengths reach the surface and how much energy is available for detection. Understanding these atmospheric effects is essential for interpreting remote sensing data accurately. When electromagnetic energy finally reaches the Earth's surface, it interacts with the target in several ways. Depending on the properties of both the target and the radiation, the energy can be absorbed, transmitted, or reflected. These interactions determine what information is available for sensors to detect. For example, a smooth surface might reflect energy in a single direction, while a rough surface scatters it in many directions. The way energy interacts with different materials helps us distinguish between them in remote sensing images, making this step vital for accurate analysis. After interacting with the target, the energy now altered needs to be captured. This is where sensors come into play. Sensors are devices that collect and record electromagnetic radiation, often from a distance. They can be mounted on satellites, airplanes, or even drones, and are designed to detect specific wavelengths of energy. The data collected by sensors forms the basis for remote sensing analysis, allowing us to create images and extract valuable information about the Earth's surface. The quality and type of sensor used greatly influence the detail and accuracy of the data obtained. Once the sensor has captured the energy, the next step is to transmit and process the data. This usually involves sending the recorded information, often electronically, to a ground station or processing center. Here, the raw data is converted into images, either digital or hard copy, that can be further analyzed. Processing may include correcting distortions, enhancing features, or combining data from multiple sources. This step is crucial for turning raw sensor readings into usable information, setting the stage for interpretation and application. After processing, the images and data are ready for interpretation and analysis. This can be done visually by experts examining the images or digitally using computer algorithms to extract patterns and information. The goal is to identify features, classify materials, and understand the conditions of the observed area. Interpretation is where the science of remote sensing meets practical application, as analysts turn data into insights that can inform decisions in fields like agriculture, forestry, urban planning, and disaster management. Final element in the remote sensing process is application. This is where all the previous steps come together to provide valuable information for real-world use. Remote sensing data is applied in a wide range of fields, from monitoring environmental changes and managing natural resources to supporting disaster response and urban development. By extracting and applying information from remote sensing imagery, we can better understand our planet, reveal new insights, and solve complex problems. The versatility of remote sensing makes it an indispensable tool in today's data-driven world. At the heart of remote sensing is electromagnetic radiation. All electromagnetic radiation has certain fundamental properties and behaves in predictable ways according to wave theory. It consists of an electric field and a magnetic field, both traveling at the speed of light but oriented at right angles to each other. Two key characteristics, wavelength and frequency, are especially important for remote sensing. Understanding these properties helps us interpret the data collected by sensors and make sense of the images produced. Wavelength is the distance between successive wave crests, usually measured in meters or its subdivisions like nanometers or micrometers. Frequency, on the other hand, refers to the number of wave cycles passing a fixed point per second, measured in hertz. These two properties are inversely related: the shorter the wavelength, the higher the frequency, and vice versa. This relationship is crucial for understanding how different types of electromagnetic radiation interact with the Earth's surface and atmosphere, and how they are detected by remote sensing instruments. Electromagnetic spectrum encompasses all types of electromagnetic radiation, from the shortest wavelengths like gamma and X-rays to the longest, such as microwaves and radio waves. For remote sensing, certain regions of the spectrum are especially useful, including ultraviolet, visible, infrared, and microwave. Each region has unique properties and interacts with the Earth's surface in different ways. By selecting the appropriate part of the spectrum, remote sensing systems can gather specific information about various features and materials. Visible spectrum is the part of the electromagnetic spectrum that our eyes can detect, ranging from about 0.4 to 0.7 micrometers. This is a very small portion compared to the entire spectrum, but it's the only one we naturally perceive as color. The visible spectrum includes violet, blue, green, yellow, orange, and red, each corresponding to specific wavelength ranges. Blue, green, and red are the primary colors, and all other colors can be formed by combining them in different proportions. Understanding the visible spectrum is essential for interpreting remote sensing images, especially those captured in true color. Beyond the visible spectrum lies the infrared region, which covers wavelengths from about 0.7 to 100 micrometers. The infrared region is divided into reflected IR and thermal IR. Reflected IR is similar to visible light and is useful for remote sensing, while thermal IR is associated with heat emitted from the Earth's surface. Sensors that detect infrared radiation can reveal information invisible to the naked eye, such as plant health or surface temperature. This makes infrared sensing a powerful tool in environmental monitoring and resource management. Microwave region of the spectrum, ranging from about 1 millimeter to 1 meter, is of growing interest in remote sensing. Microwaves have the longest wavelengths used in remote sensing and can penetrate clouds, rain, and even vegetation to some extent. This makes microwave sensors especially valuable for applications like weather monitoring, soil moisture estimation, and disaster assessment. Unlike visible and infrared radiation, microwaves can be used day or night and in all weather conditions, greatly expanding the capabilities of remote sensing systems. Before electromagnetic radiation reaches the Earth's surface, it must pass through the atmosphere, where it can be scattered or absorbed by particles and gases. Scattering occurs when radiation is redirected by small particles or molecules, while absorption happens when certain gases take up energy at specific wavelengths. These processes can significantly affect the amount and type of energy that reaches the ground and is detected by sensors. Understanding atmospheric interactions is essential for correcting and interpreting remote sensing data. There are three main types of scattering in the atmosphere: Rayleigh, Mie, and non-selective scattering. Rayleigh scattering occurs when particles are much smaller than the wavelength of radiation, causing shorter wavelengths like blue light to scatter more. This is why the sky appears blue. Mie scattering happens when particles are about the same size as the wavelength, affecting longer wavelengths and dominating in cloudy conditions. Non-selective scattering occurs with particles much larger than the wavelength, scattering all wavelengths equally and making clouds appear white. Each type of scattering influences the quality and interpretation of remote sensing data. Absorption is another key atmospheric process, where gases like ozone, carbon dioxide, and water vapor absorb electromagnetic energy at specific wavelengths. Ozone absorbs harmful ultraviolet radiation, carbon dioxide traps heat in the infrared region, and water vapor absorbs both long-wave infrared and short-wave microwave radiation. The presence and concentration of these gases vary by location and time, influencing which parts of the spectrum are available for remote sensing. The regions of the spectrum not heavily affected by absorption are known as atmospheric windows, which are especially important for remote sensing applications. Atmospheric windows are regions of the electromagnetic spectrum where the atmosphere is mostly transparent, allowing radiation to pass through with minimal absorption. These windows are crucial for remote sensing, because they define the wavelengths that sensors can effectively use to observe the Earth's surface. By comparing the characteristics of energy sources like the Sun and the Earth with the available atmospheric windows, scientists can select the optimal wavelengths for different remote sensing applications. When radiation that has passed through the atmosphere reaches the Earth's surface, it can be absorbed, transmitted, or reflected by the target. The proportions of each interaction depend on the wavelength and the material's properties. Absorption means the energy is taken in by the target, transmission means it passes through, and reflection means it bounces off. In remote sensing, reflected energy is often the most important, as it is what sensors typically measure. Understanding these interactions is key to interpreting remote sensing images. Reflection from a surface can be either specular or diffuse. Specular reflection occurs when the surface is smooth, causing energy to reflect in a single direction like a mirror. Diffuse reflection happens when the surface is rough, scattering energy in many directions. Most natural surfaces fall somewhere between these two extremes. The type of reflection depends on the surface roughness relative to the wavelength of the incoming radiation. This distinction is important for interpreting remote sensing images, as it affects how features appear. Different materials interact with radiation in unique ways. For example, leaves contain chlorophyll, which absorbs red and blue wavelengths but reflects green, making leaves appear green in summer. In the near-infrared, healthy leaves are excellent diffuse reflectors, which is why scientists use near-IR reflectance to assess vegetation health. Water, on the other hand, absorbs longer wavelengths and reflects shorter ones, making it appear blue or blue-green. The presence of sediment or algae can change the color and brightness of water in remote sensing images. These examples show how spectral responses help us distinguish between different surface features. The amount of solar radiation reflected, absorbed, or transmitted by a material varies with wavelength. When we plot the intensity of reflected energy across different wavelengths, we get a spectral response curve or signature. These curves are unique for different materials and help us identify and distinguish between them in remote sensing images. For example, vegetation, soil, water, and urban areas each have distinct spectral signatures, allowing for accurate classification and analysis. Comparing the spectral signatures of different materials, we can distinguish between them even if they look similar in visible light. For instance, sand and vegetation may reflect similar amounts of energy at one wavelength but differ greatly at another. This principle allows remote sensing systems to classify land cover types, monitor changes, and detect specific features by analyzing reflectance at multiple wavelengths. The ability to measure and compare spectral responses is a powerful tool in environmental science and resource management. Remote sensing systems can be classified as passive or active. Passive sensors detect naturally available energy, usually from the sun, and can only operate when this energy is present, typically during daylight hours. Active sensors, on the other hand, provide their own energy source, such as radar or laser, allowing them to operate day or night and in all weather conditions. Each type has its advantages and is suited to different applications. Understanding the difference between passive and active sensing is key to choosing the right system for a given task. Passive sensors, such as radiometers, detect electromagnetic radiation that is naturally emitted or reflected by objects. These sensors are sensitive to specific wavelengths and can record data as digital numbers, which are then processed into images. The spatial resolution of a passive sensor depends on its instantaneous field of view (IFOV), which determines the size of the area each pixel represents. The swath width, or the ground area covered by the sensor, is determined by the angular field of view. Passive sensors are widely used in environmental monitoring, agriculture, and land use studies. Mechanical scanning radiometer, also known as a whisk broom sensor, uses an oscillating or rotating mirror to direct incoming radiation onto a detector. The detector collects energy as a series of scan lines perpendicular to the flight path. The collected energy is converted into electrical signals, which are recorded in digital format for further processing. This type of sensor is commonly used in satellite and airborne remote sensing, providing detailed images for analysis. Push broom radiometer uses a wide-angle optical system to image all scenes across the field of view simultaneously, without any mechanical movement. As the sensor moves along its flight path, successive lines are imaged and sampled for transmission. This system offers advantages like reduced noise, no moving parts, and high geometric accuracy. Push broom sensors are widely used in modern remote sensing platforms for their efficiency and reliability. Active sensors, such as radar and lidar, emit their own energy toward the target and measure the reflected signal. This allows them to operate independently of sunlight and in various weather conditions. Imaging radars like synthetic aperture radar (SAR) are used to create detailed images of the Earth's surface, even through clouds or at night. Active sensors are essential for applications where passive sensing is limited, such as mapping terrain, monitoring deforestation, or assessing disaster impacts. Spatial resolution refers to the smallest feature that can be detected in an image. It depends on the sensor's distance from the target and its instantaneous field of view (IFOV). Higher spatial resolution means finer detail but usually covers a smaller area. For example, satellite images may show entire regions, while aerial photos can reveal individual buildings or cars. Understanding spatial resolution is important for selecting the right data for specific applications, whether you need a broad overview or detailed analysis. Each remote sensing image is made up of pixels, which are the smallest units of the image. Pixel size represents the area on the ground covered by each pixel. It's important to distinguish between pixel size and spatial resolution. They are related but not always the same. The scale of an image refers to the ratio of distance on the image to actual ground distance. High-resolution images have small pixel sizes and can show more detail, while low-resolution images cover larger areas but with less detail. Images with only large features visible are said to have coarse or low resolution, while those showing small objects have fine or high resolution. Military and research sensors often aim for the highest possible resolution to capture maximum detail. Commercial satellites offer a range of resolutions, from a few meters to several kilometers. The choice between coarse and fine resolution depends on the application. Broad surveys may use coarse resolution, while detailed studies require fine resolution. Spectral resolution describes a sensor's ability to distinguish fine wavelength intervals. The finer the spectral resolution, the narrower the wavelength range for each channel or band. Black and white film has coarse spectral resolution, recording all visible wavelengths together. Color film has higher spectral resolution, distinguishing between blue, green, and red wavelengths. Modern remote sensing systems use multispectral or hyperspectral sensors, which can detect dozens or even hundreds of narrowbands, allowing for detailed analysis and discrimination between different materials. Adiometric resolution refers to a sensor's ability to detect slight differences in energy. It's determined by the number of bits used to record data, which defines the range of possible digital values. For example, an 8-bit sensor can record 256 levels of brightness, while a 4-bit sensor can only record 16. Higher radiometric resolution allows for more detailed and nuanced images, making it easier to distinguish subtle differences between features. This is especially important in applications like vegetation monitoring or water quality assessment. Temporal resolution describes how often a sensor can revisit and collect data for the same location. High temporal resolution means frequent observations, which is important for monitoring changes over time, such as crop growth, deforestation, or urban expansion. Some satellites can provide daily images, while others may revisit the same area only every few days or weeks. Choosing the right temporal resolution depends on the dynamics of the phenomena being studied. Remote sensing, the term image refers to any pictorial representation, regardless of the wavelengths or device used. A photograph specifically means an image recorded on photographic film, usually in the visible or reflected infrared range. With advances in technology, photographs can be digitized, turning them into digital images composed of pixels. Both forms convey similar information, but digital images offer more flexibility for analysis and processing. Digital images are created by dividing a photograph, or seen in small equal-sized areas called pixels. Each pixel is assigned a digital value representing its brightness. Computers display these values as different shades of gray or color, depending on the data. Sensors that record electromagnetic energy electronically produce digital images directly, making it easy to analyze and manipulate the data. This digital approach is the foundation of modern remote sensing. Remote sensing sensors often collect data in specific wavelength ranges, known as channels or bands. Each channel records information from a narrow range of wavelengths, which can be combined to create color images or analyzed separately for detailed studies. By using multiple channels, sensors can capture more information about the Earth's surface, revealing features that might be invisible in a single band. This multi-channel approach is key to the power of remote sensing. Remote sensing data can be displayed in various ways. A single channel can be shown as a black and white image, with different shades representing different brightness levels. When multiple channels are combined, each assigned to a primary color red, green, or blue, the result is a color image that can reveal more detail and information. This method allows analysts to visualize and interpret complex data more easily, supporting a wide range of applications. Spectral signatures are used in practice to identify and classify different materials on the Earth's surface. By measuring reflectance at multiple wavelengths, analysts can distinguish between vegetation types, soil, water, and urban areas. This technique is widely used in agriculture, forestry, geology, and environmental monitoring. The ability to recognize unique spectral signatures is one of the most powerful aspects of remote sensing. Multispectral sensors collect data in several broad wavelength bands, while hyperspectral sensors can detect hundreds of very narrow bands. Hyperspectral sensors provide extremely detailed information, allowing for fine discrimination between different materials. These advanced sensors are used in research, mineral exploration, and precision agriculture, offering new possibilities for analysis and discovery. Bit depth of a sensor determines how many brightness levels it can record. Higher bit depth means more levels and greater detail in the image. For example, an 8-bit image can display 256 shades of gray, while a 16-bit image can show over 65,000. This increased detail is important for detecting subtle differences in features and improving the accuracy of analysis. Selecting the appropriate spatial, spectral, radiometric, and temporal resolution is critical for successful remote sensing projects. The choice depends on the goals of the study, the features of interest, and the available resources. High-resolution data may be needed for detailed mapping, while lower resolution may suffice for broad surveys. Understanding the trade-off between different types of resolution helps ensure the best results for any application. In summary, remote sensing is a powerful tool for observing and understanding the Earth's surface without direct contact. By harnessing electromagnetic radiation, sensors, and advanced processing techniques, we can gather detailed information about our planet. Key concepts include the electromagnetic spectrum, atmospheric interactions, spectral signatures, and various types of resolution. Mastering these fundamentals opens up a world of possibilities for research, management, and discovery. As technology advances, remote sensing continues to evolve, offering new capabilities and applications. From monitoring climate change to supporting disaster response, the insights gained from remote sensing are more valuable than ever. By understanding the principles and techniques covered in this unit, you're well equipped to explore further and make the most of this exciting field. Stay curious and keep exploring the world through the lens of remote sensing.